In the past few lectures, we've seen a series of tools for helping us create procedures to compute a variety of computational processes. Before we move on to more complex issues in computation, it's useful to step back and look at the more general issues involved in the process of actually creating procedures. In particular, we want to spend a little bit of time talking about good programming practices. This sounds a little bit like lecturing about motherhood and apple pie. That is, a bit like talking about things that seem obvious, apparent, and boring in that everybody understands and accepts them. However, it's surprising how many, quote, experienced, end quote, programmers don't execute good programming practices, and we want to get you started on the right track. Thus, in this lecture, we're going to look briefly at several methodological aspects of creating procedures: designing the components of our code, debugging our code when it doesn't run correctly, writing documentation for our code, and testing our code. We'll highlight some standard practices for each stage and indicate why these practices lead to efficient and effective generation of code. Let's start with the issue of how to design code, given a problem statement. There are many ways to do this, but most of them involve some combination of the following steps: design of data structures, design of computational modules, and design of interfaces between the modules. Once we've laid out the general design of those stages, we follow by creating specific instantiations of the actual components. Now, we've not yet talked about data structures in Scheme, and we'll return to that issue in a few lectures. For our purposes here, the key thing to note is that when designing a computational system, it is extremely valuable to decide what kinds of information naturally should be grouped together, and to then create structures that perform that grouping, while maintaining interfaces to the structures that hide the details. For example, one thinks naturally of a vector as a pairing of an x and y coordinate. One wants to be able to get out the coordinates when needed, but in many cases one thinks naturally of manipulating a vector as a unit. Similarly, one can imagine aggregating together a set of vectors to form a polygon. And again, one can think of manipulating the polygon as a unit. Thus, a key stage in designing a computational system is determining the natural data structures of the system. A second stage in designing a computational system is deciding how best to break the computation into modules or pieces. This is often as much art as science, but there are some general guidelines that help us separate out modules in our design. For example, is there part of the problem that defines a computation that is likely to be used many times? Are there parts of the problem that can be conceptualized in terms of their behavior? For example, how they convert certain inputs into certain types of outputs, without worrying about the details of how it is done. Does this help us focus on other parts of the computation? Or said a bit differently, can one identify parts of the computation in terms of their role, and think about that role in the overall computation without having to know details of the actual computation? If one can, these components are then good candidates for separate modules or components of the design, since we can focus on their use while ignoring the details of how they actually achieve that computation. Finally, given that one can identify data structures, whose information is to be manipulated, and stages of computation, in which that information is transformed, one wants to decide the overall flow of information between the modules. What types of inputs does each module need? What types of data does each module return? How does one ensure that the correct types are provided in the correct order? These kinds of questions need to be addressed in designing the overall flow between the modules. This is perhaps more easily seen by thinking about an example. And in fact, you've already seen one such example, our implementation of squirt. When we implemented our method for square roots, we actually engaged in many of these stages. We didn't worry about data structures, since we're simply interested in numbers. We did, however, spend some effort in separating out modules. Remember, our basic computation was, we start with a guess. If it's good enough, we stop. Otherwise, we make a new guess by averaging the current guess and the ratio of the target number and the guess, and continue. To design this system, we separated out several modules. The notion of averaging, the notion of measuring good enough, for example. We saw that some of these modules might themselves rely on other procedural abstractions. For example, our particular version of good enough needed to use the absolute value procedure, though other versions might not. Once we had separated out these notions of different computations, average and good enough, we considered the overall flow of information through those modules. Note, by the way, that we can consider each of these processes as a black box abstraction, meaning that we can focus on using these procedures without having to have already designed the specific implementation of each. Now, what about the flow between these modules? In our case, we began with a guess and tested to see if it was good enough. If it was, we could then stop and just return the value of the guess. If it was not, then we needed to average the current guess and the ratio of our target number to the guess. And then we needed to repeat the entire process with this new value as our new guess. The point of laying out these modules, or black boxes, is that we can then use them to decide how to divide up the code and how to isolate details of a procedure from its use. As we saw when we implemented our squirt procedure, we can change details of a procedure, such as average, without having to change any of the procedures that use that particular component. As well, the flow of information between the modules helps guide us in the creation of the overall set of procedures. Thus, when faced with any new computational problem, we want to try to engage in the same exercise. Block out chunks of the computation that can be easily isolated, identify the inputs and outputs from each chunk, and lay out the overall flow of information through the system. Then we can turn to implementing each of the units separately and testing the entire system while isolating the effects of each unit. A second key element to good programming practice is code documentation. Unfortunately, this is one of the least well-practiced elements. Far too often programmers are in such a hurry to get things written that they skip by the documentation stage. While this may seem reasonable at the time of code creation, when the design choices are fresh in the program creator's mind, 6 months later when one is trying to read the code, even one's own, it may be very difficult to reconstruct why certain choices were made. Indeed, in many commercial programming settings, more time is spent on code maintenance and modification than on code generation. Yet without good documentation, it can be very difficult or inefficient to understand existing code and change it. As well, good documentation can serve as a valuable source of information about the behavior of each model, enabling a programmer to maintain the isolation of the details of the procedural abstraction from the use of that abstraction. This information can be helpful when actually debugging procedures. As with designing procedural modules, the creation of good documentation is unfortunately as much art as science. Nonetheless, here are some standard elements of well-documented code. We're going to illustrate each of these with a specific example. First, describe the goal of the procedure. Is it intended to be part of some other computation, as this helper function is? If so, what is the rough description of the process? Note that here we've been a bit cryptic in order to fit things on the slide, and we might well want to say more about successive refinement, though we could defer that to the documentation under the improved procedure. We also identify the role of each argument to the procedure right up. Second, describe the types of values used in the computation. In this case, the inputs or parameters are both numbers, and the return value is also a number. Notice the format we've used here to specify that. Actually, if we want to be more careful, we could require that x be a positive number, and we'd place a check somewhere to ensure that this is actually true. Third, describe constraints, either desired or required, on the computation. Here, we know that squaring the guess should get us something close to the target value, although we really don't guarantee this until we reach the termination stage. And fourth, describe the expected state of the computation and the goal of each stage in the process. For example, here we indicate what good enough should do, namely test if our approximation is sufficiently accurate. Then we indicate that if this is the case, we can stop and what value to return to satisfy the contract of the entire procedure. And we indicate how to continue the process, though we could probably say a bit more about what improve should do. Notice how we can use the documentation to check some aspects of our procedure's contract. Here, we have indicated that the procedure should return a number. By examining the if expression, we can see that in the consequent clause, if the input parameter guess is a number, then we're guaranteed to return a number. For the alternative clause, we can use induction to reason that given numbers as input, we also return a number, and hence the entire procedure returns a value of the correct type. In general, taking care to meet each of the stages when you create code will often ensure an easier time when you have to refine or replace code. Getting into the habit of doing this every time you write something, even if you're only minutes away from some problem set deadline, will greatly improve your productivity. While we would like to believe that the code we will write will always run correctly, first time we try it, experience shows that this is a fortunate happenstance. Typically, especially with complex code, things will not work right, and we need to debug our code. Debugging is in part an acquired skill. With lots of practice, you will develop your own preferred approach. Here, we're going to describe some of the common sources of errors in code and standard tools for finding the causes of errors and fixing them. A common and simple bug in code arises when we use an unbound variable. From the perspective of scheme, this means that somewhere in our code we try to reference, or look up the value of, a variable that does not have one. This can occur for several reasons. The simplest is that we mistyped, a spelling error. The solution in this case is pretty straightforward. Simply search through the code file using editor tools to find the offending instance and correct it. Sometimes, however, we are using a legal variable, that is, one that we intended to hold some value, but the evaluator still complains that this variable is unbound. How can that be? Remember that in Scheme, a variable gets bound to a value in one of several ways. We may define it at top level. That is, we may directly tell the interpreter to give a variable some value. We may define it internally within some procedure. Or we may use it as a formal parameter of a procedure, in which case it gets locally bound to a value when the procedure is applied. In the last two cases, if we attempt to reference the variable outside the scope of the binding, that is, somewhere outside the bounds of the lambda expression in which the variable is being used, we will get an unbound variable error. This means that we have tried to use a variable outside its legal domain, and we need to correct this. This probably means we have a coding error, but we can isolate the problem either by searching for instances of the variable in the code file or by using the debugger. So what does the debugger do to help us find errors? Each programming language will have its own flavor of debugger. For an interpreted language like Scheme, the debugger actually places us inside the state of the computation. That is, when an error occurs, the debugger provides us access to the state of the computation at the time of the error, including access to the values of the variables within the computation. Moreover, we can step around inside the environment of the computation. We can work back up the chain of computational steps, examining what values were produced during reductions, where computation is reduced to a simpler expression, and examining what values were produced during subproblems, where the computation was converted to a simpler version of itself. For example, here is a simple procedure, which we have called with argument 2. Notice what happens when we hit the unbound variable error and enter the debugger. We are placed at the spot in the computation at which the error occurred. If we choose to step back through the chain of evaluations, we can see what expressions were reduced to get to this point, and what recursive versions of the same problem were invoked in reaching this point. In this case, we note that foo was initially called with argument 2, and after a reduction through an if expression, we arrived at an expression that contained within it a simpler version of that same problem. This reduction stage repeated again until we apparently reached the base case of the if expression, where we hit the unbound variable. We can see in this example that our unbound variable is coming from within the body of foo and is in the base case of the decision process. A second class of errors deals with mistakes in syntax, creating expressions that do not satisfy the programming language's rules for creating legal expressions. A simple one of these is an expression in which the wrong number of arguments is provided to the procedure. If this occurs while attempting to evaluate the offending expression, we will usually be thrown into the debugger, a system again intended to help us determine the source of the error. In Scheme, as we've seen, the debugger provides us with information about the environment in which the offending expression occurred. And it has those tools we saw for examining values associated with variable names and for examining the sequence of expressions that have been evaluated leading up to this error. By stepping through the frames of the debugger, just as we did before, we can again isolate where in our code the incorrect expression resides. A more insidious syntax error occurs when we use an expression of the wrong type somewhere in our code. If we use an expression whose value is not a procedure as the first sub-expression of a combination, we will get an error that indicates we have tried to apply a non-procedure object. As before, the debugger can often help us isolate the location of this error, though it may not provide much insight into why an incorrect object was used as a procedure. For that, we may have to trace back through our code to determine how this value was supplied to the offending expression. The harder error to isolate is one in which one of the argument expressions to a combination is of the wrong type. The reason this is harder to track down is that the cause of the creation of an incorrect object type may have occurred far upstream. That is, some other part of our code may have created an incorrect object which has been passed through several levels of procedure calls before causing an error. Tracking down the original source of this error can be difficult, as we need to chase our way back through the sequence of expression evaluations to find where we accidentally created the wrong type of argument. The most common sorts of errors, though, are structural ones. This means that our code is syntactically valid, composed of correctly phrased expressions, but the code does not compute what we intended, because we've made an error somewhere in the code design. This could be for a variety of reasons. We started a recursive process with the wrong initial values, or we're ending at the wrong place, or we're updating parameters incorrectly, or we're using the wrong procedure somewhere, and so on. Finding these errors is tougher, since the code may run without causing a language error, but the results we get are erroneous. This is where having good test cases is important. For example, when testing a recursive procedure, it's valuable to try it using the base case values of the parameters to ensure the procedure is terminating at the right place and returning the right value. It is also important to select input parameter values that sample or span the range of legal values. Does it work with small values, with large values? Does changing the input value by a small increment cause the expected change in the output value? And what do we do if we find we have one of these structural errors? Well, our goal is to isolate the location of our misconception within the code. And to do this, there are some standard tools. The most common one is to use a print or display expression. That is, to insert into our code expressions that will print out for us useful information at different stages of the computation. For example, we might insert a display expression within the recursive loop of a procedure, which will print out information about the values of the parameters. This will allow us to check that parameters are being updated correctly, and that end cases are correctly seeking the right termination point. We might similarly print out the values of intermediate computations within recursive loops, again to ascertain that the computation is operating with the values we expect and is computing the values we expect. A related tool, supplied for example with Scheme, is a tracer. This allows us to ask the evaluator to inform us about the calling conventions of procedures. That is, to print out the values of the parameters supplied before each application of the procedure we designate, and the value returned by each procedure call. This is similar to our use of display expressions, but is handled automatically for us. It applies only to parameters of procedure calls, however, so that if we want to examine some detailed states of the computation, we need to fall back on the display tactic. In some cases, it may help to actually walk through the substitution model, that is, to see each step of the evaluation. Many languages, including Scheme, provide a means for doing this. In our case, it's called the stepper. This is a mechanism that lets us control each step of the substitution model in the evaluation of an expression. It is obviously tedious, but works best when we need to isolate a very specific spot at which an error is occurring, and we don't want to insert a ton of display expressions. Perhaps the best way to see the role of these tools is to look at an example, which we do. Let's use an example of a debugging session to highlight these ideas. This will be primarily to fix a structural error, but we'll see how the other tools come into play as we do this. Suppose we want to compute an approximation to the sine function. Here's a mathematical approximation that will give us a pretty good solution. Let's try coding this up. So here's a first attempt at some code to do this. We will assume that fact and small enough already exist. The basic idea behind this procedure is quite similar to what we did for square roots. We start with a guess. We then see how to improve the guess, in this case by computing the next term in the approximation, which we would like to add in. If this improvement is small enough, we're done and we can return to the desired value. If not, we repeat the process with a better guess by adding in the improvement to the current guess. Now, let's try it out on some test cases. One nice test case is the base case of x equal to 0. That clearly works. Another nice test case is when x is equal to pi, where we know the result should also be close to 0. Oops, that didn't work. Nor does the code work for pi half as a value for x. Both of these latter cases give results that are much too large. Okay, we need to figure out where our conceptual error lies. Let's try to isolate this by tracing through the computation. In particular, we will add some display expressions that will show us the state of the computation each time through the recursion. And let's try this again. Here we've used the test case of x equal to pi, and we can see the trace of the computation. If we compare this to the mathematical equation, we can see one problem. We really only want terms where n is odd, but clearly we're getting all terms for n. So we need to fix this. Most likely this is because we're not changing our parameters properly. So here's the correction. We will need to increment our parameter by 2 each time, not by 1. An easy mistake to make and to miss. So let's try this again. We've gotten better as we're only computing the odd terms for n, but we're still not right. If we look again at the mathematical equation, we can see that we should be alternating signs on each term. Or said another way, the successive approximations should go up, then down, and so on. Note that we could have also spotted this if we had chosen to display the value of next at each step. So, we need to keep track of some additional information. In this case, whether the term should be added or subtracted from the current guess. Well, we can handle that. We add another parameter to our helper procedure, which keeps track of whether to add the term, if the value is 1, or whether to subtract the term, if the value is -1. And of course, we will need to change how we update the guess and how we update the value of this parameter, as shown. Oops, we blew it somewhere. We could enter the debugger to locate the problem, but we can already guess that since we changed the aux procedure, That must be the cause of getting this particular error. And clearly the solution is to make sure we call this procedure with the right number of arguments. Notice that in this case it is easy to spot this error, but in general we should get into the habit of checking all calls to a procedure when we alter its set of parameters. Now, if we try this on the test case of x equal pi, it works. But if we try it on the test case of pi half, it doesn't. The answer should be close to 1, but we're getting something close to -1. Note that this reinforces why we want to try a range of test cases. If we'd stopped with just x equal pi, we would not have spotted this problem. So how do we fix it? Here's the bug. We started with the wrong initial value, a common error. By fixing this to the right initial value, we can try again, and finally we get the right performance. Note how we've used printing of values to isolate changes, as well as using the debugger to find syntax errors. In general, we want you to get into the habit of doing the same things. Developing good programming methodology habits now will greatly help you when you have to deal with large, complex bodies of code. Good programming discipline means being careful and thorough in the creation and the refinement of code of all sizes and forms. So start exercising your programming muscles now. One other tool that we have in our armamentarium of debugging is the use of types. In particular, type specifications, that is, constraints on what types of objects are passed as arguments to procedures and what types of objects are returned as values by procedures, can help us both in planning and designing code and in debugging existing code. Here we're going to briefly explore both of these ideas to demonstrate why careful programming practice can lead to efficient generation of robust code, and to illustrate why thinking about types of procedures and objects is a valuable practice. To motivate the idea of types as a tool in designing code, let's consider an example. Suppose we want to create a procedure called repeated that will apply any other procedure some specified number of times. Since this is a vague description, let's look at a specific motivating example. We saw earlier the idea that we could implement multiplication as a successive set of additions, and that we could implement exponentiation as a successive set of multiplications. If we look at these two procedures, we can see that there's a general pattern here. There is a base case value to return, 0 in one case, 1 in the other. And there is the idea of applying an operation to an input value and the result of repeating that process one fewer times. Repeated is intended to capture that common pattern of operation. So here's what we envision. We want our repeated procedure to take a procedure to repeat and the number of times to repeat it. It should return a procedure that will actually do that when applied to some value. Here we can see that the procedure being applied would change in each case, and the initial value to which it would apply would change. But otherwise, the overall operation is the same. The question is, how do we create repeated, and why does the call to repeated have that funny structure with 2 open parens instead of 1? First, what is the type of repeated? Well, from the previous slide, we know that as given, it should take 2 arguments. The first should be a procedure of 1 argument. We don't necessarily know what type of argument this procedure should take. In the 2 examples shown, the input was a number, but we might want to be more general than this. What we do know is that whatever type of argument this procedure takes, it needs to return a value of the same type, since it is going to apply that procedure again to that value. Hence, the first argument to repeated must be a procedure of type A maps to A. The second argument to repeated must be an integer, since we can only apply an operation an integer number of times. Actually, it should probably be a non-negative integer. And as we argued, the returned object needs to be a procedure of the same type, A maps to A, because the idea is to use repeated recursively on its. Okay, now how does this help us in designing the actual procedure? We know the rough form that repeated should take. It should have a test for the base case, which is when there are no more repetitions to make. In the base case, it needs to do something, which we have to figure out. And in the recursive case, we expect to use repeated to solve the smaller problem of repetition, plus some additional operations, which we also need to figure out. For the base case, what do we know? Well, we know that by the type information, this must return a procedure of a single argument that returns a value of the same type. We also know that if we're in the base case, there's really nothing to do. We don't want to apply our procedure any more times. Hence, we can deduce that we need to return a procedure that serves as the identity. It simply returns whatever value was passed in. Now, what about the recursive case? Well, the idea is to apply the input procedure to the result of repeating the operation n-1 times. How do we use this idea to figure out the correct code? First, we know that whatever we write must have type A maps to A by the specification of repeated. Next, we know that we want to apply the input procedure proc to the result of solving the same problem n-1 times. So we ought to have something that has these pieces in it. But let's check the types. We know that repeated has type A maps to A, and the proc expects only an argument of type A. So clearly we need to apply repeated to an argument before passing the result on to proc. Hence we have the form shown. Note how this fairly complex piece of code can be easily deduced by using types of procedures to determine interactions. Of course, to be sure that we did it right, we should now test this on some test cases, for example by running mul or exp on known cases. A second way that types can help us is in debugging code. In particular, we can use the information about types of arguments and types of return values explicitly to check that procedures are interacting correctly. And in some cases, where there are constraints on the actual values being returned, we can also enforce a check. As an example, here is our squirt code from before. One of the conditions we have is that the input arguments need to be numbers. And we could check that numbers are being correctly passed in by inserting an explicit check. In this case, it's probably redundant since the only code that calls squirt helper is itself, but in general, when multiple procedures might be involved, you can see how this check is valuable. Note that one can insert this check only when debugging, as a tool for deducing what procedure is incorrectly supplying arguments, but one can also use it regularly if you want to ensure robust operations of the code. Clearly, one could also add a check on the return value in a similar fashion. There are other things one could use to ensure correct operation as well. For example, the number whose square root we are seeking should be a positive number, and we could check this as shown before we proceed. Thus we see that types also serve as a useful tool in good programming methodologies. To summarize, we've seen in this lecture a set of tools for good programming practices, ways of designing code, debugging code, evaluating and testing code, and using knowledge of code structure to guide the design. Let's start by revisiting lists. Remember that we said a list was simply a sequence of const cells connected by couters ending in an empty list, also known as nil. Remember that we said lists also had the property of closure. If we were to const anything onto the beginning of the list, we would get a new sequence of const cells ending in the empty list, hence a list. And, with the exception of the empty list, taking the couter of a list results in a sequence of const cells ending in the empty list, hence a list. Note that this is really something that has an inductive flavor to it. The base case is an empty list. Given that every collection of const cells of size less than n ending in an empty list is a list, then clearly putting or consting a new element onto such a list yields a list, and thus by induction, every collection of const cells ending in the empty list is a list. We should be able to use this idea to reason about procedures that manipulate lists. Here is one of our standard procedures for manipulating lists, our old friend map. Intuitively, we know how this code should work, but can we establish formally that it does what we expect? Sure. We just use our notion of induction here, both on the data structure and on the code itself. For the base case, we have the base case data structure for a list, namely an empty list. Thus, the code clearly returns the right structure. Now, assume that map correctly returns a list in which each element of the input list has had proc applied to it, and that the order of the elements is preserved for any list of size smaller than the current one. Then, we know, given list, that by induction on the data structure, couter of list is a list. Further, by induction on the procedure map, we know this will return a list of the same size, with each element replaced by the application of proc to that element. We can then process the first element of the new list, and by induction on the data structure, const will return a new list of the appropriate size that also satisfies the conditions of map. Thus, by induction, we know that map will correctly perform as expected. Now, is there anything explicit in the code that says this applies only to lists of numbers? Of course not. It could be lists of symbols or lists of strings, or lists of anything. That can be seen by looking at the type definition for a list. As with pairs, we will represent a list by the symbol list followed by angle brackets containing a type definition for the elements of the list. Since lists are created out of pairs, we can be more explicit about this definition by noting that a list of some type is either a pair whose first element is of that type and whose second element is a list of the same type, or, which is indicated by that vertical bar, the list is the special empty list. Note the nice recursive definition of a list with the closure property that the couter of a list itself is a list. Also notice that nothing in this type definition says the elements hanging off of the cars of the list have to be numbers. In fact, our definition uses the arbitrary type C. This means that those structures could be anything, including other lists. This leads nicely to a more general data structure called a tree, which lets us capture much more complex kinds of relationships and structures. So, what does a tree look like, and are there common procedures associated with the manipulation of trees? First, here's the conceptual idea behind a tree. A tree is a structure that consists of a root, or a starting point. At the root, and indeed at every other point in the tree, are a set of branches that connect different parts of the tree together. You can see this shown here. Each branch is said to contain a child or a subtree, and that subtree could itself be another tree or could terminate in a leaf. In the example shown here, the leaves are all numbers, but it could be, of course, other things like symbols or other structures. Note that there's a nice recursive property to a tree. That is, taking a subtree gives us, in fact, again, a tree. That is, taking any of these branches leads to a structure that looks exactly like a tree. This suggests that procedures to manipulate trees are going to have this nice recursive property as well. To implement a tree, we can just build it out of lists. In fact, each level of the tree will be a list. The elements of each of the branches will be shown as the cars of that top level list. And those levels themselves may contain subtrees. So in the example shown here, the first branch is just the leaf 2. The second branch is itself a subtree, so there's another list with things hanging off of it. And the third branch is again just the leaf 4. So we have lists of lists as our implementation of a tree. So what can we say about a tree? First, we can define its type. Very similar to a list, we have that a tree of type C, meaning a tree whose elements are of some type C, has the property that it's constructed as a list whose elements themselves are trees of type C, or as a leaf of type C. And a leaf of type C is just this type itself, C. In fact, as we define it here, it suggests that C, the type of the elements, would always be the same, a tree of numbers or a tree of symbols. Clearly, we could generalize this, but for now, this will serve as a good type definition. So to repeat, a tree whose elements are of type C is implemented as a list of elements, each of which is itself a tree, or as a leaf. Now, associated with a tree, we expect to see some standard operations. One of them is a predicate, which we'll call leaf, which will tell us whether we're at a subtree that is itself a leaf or whether there's more things to test. The second thing we want to see, though, is how different operations can be used to apply to elements of a tree. We expect to see a similar form to what we saw with lists, but more general, to deal with the fact that the elements hanging off of the structure may not be simple primitives like numbers, but may themselves be complex things like trees. So given that we have a tree as a data structure built out of lists of lists, what kinds of things can we do with it? What kinds of procedures should we expect to see to manipulate trees? First of all, since a tree is implemented as a list, in principle we could just use list procedures on them, although that starts to border on infringing on the data abstraction of the tree itself. Let's see what happens if we do it. Here I've defined a simple little tree. Call it my tree. It's a list of lists, and there's the structure shown in box and pointer diagram. Now, let's suppose we ask for the length of this structure. Remember, length is a procedure that applies to lists. We can certainly apply it to my tree, and it returns 3. Now, that may not be what you would have expected when we asked for the length. Somehow, length sort of should count the number of elements or the leaves of the tree, but it only returned 3. Why? Well, clearly length applies to a list, and since a tree happens to be implemented as a list of lists, it just counts the number of elements at the top level list of that data structure. That is, it counts the first car, 4, the second car, which happens to be a list, and the third car, 2, to get 3 things. This may actually be okay if I simply want to know the number of elements at the top level of the tree, but suppose I actually want to count elements in the tree itself. How do I do it? In particular, suppose I want a procedure, let's call it count leaves, that will count all the elements that are leaves in this tree, that is, all the numbers. Ideally here, this should return the value 4. I need to build a procedure that takes advantage of the data structure of the tree directly to do that. So let's think about how to do that. And remember, the goal here isn't just to come up with something that deals with trees. It's to use the general idea of writing procedures to go hand in hand with data structures that we're trying to see. Nonetheless, for counting the number of leaves in the tree, we can come up with a pretty good strategy. What do we have? Well, certainly we have a base case that says if we've got an empty tree, the answer is 0. There are no leaves. We also have a second base case, which is a little different than what we've seen before. The second base case says if we're counting a tree that just consists of a leaf, obviously there's 1 leaf there. and then the recursive strategy. And here we need to be careful. When we were dealing with lists, recursive strategies said do something to the car of the list and then add that into whatever you do with the other parts of the list, the cdr of the list. Remember now that a tree has a number of children hanging off of it. So the count of the number of things in a tree will be the sum of how many leaves I count in each child of the tree. And that will include dealing with all of the different possible subchildren that hang off of it. So let's build it. Here's my definition for count leaves. It takes in one data structure, a tree, and it has several cases. It has the two base cases. If the tree is empty, using null to check for it, then the answer is 0. If the tree is a leaf, using my predicate for a leaf, then the answer is 1. Otherwise, I get what I have in terms of counting the number of leaves in the first part of the tree and adding that to getting what I get by counting the number of leaves in the rest of the tree. Different form here than what we've seen before. Right? In the past, we would have just done something with the car of the tree and recursively used count leaves on the cdr of the tree if we were treating this like a list. But since the car of the tree could itself be a tree and not just an element, I have to go ahead and count the leaves in that part of the tree as well. You should stop and think about what kind of orders of growth we're going to see for this kind of procedure. Notice it has 2 calls to count leaves in its recursive case, and that should remind you of a kind of structure we've seen before. And then to make this work, I just need to define leaf. That's a predicate that says, is this an element or not? And that's easy. I'll first check to see if it's a pair. If it is, then it can't be a leaf because it's part of the tree. And so I'll use not of pair to implement my notion of a leaf predicate. Step back for a second. Notice how, again, the definition of this procedure reflects the structure of the tree. Here, at each level, I have a choice. I have 2 branches, down one half or down the other half of the tree. And that means I need 2 recursive calls to deal with the structures hanging below it. Compare that, as we've already suggested, to the kinds of procedures we had that worked with lists, where in fact we had 1 recursive call plus something to deal with the first element. This message is one we're going to repeat many times. The recursive structure of the procedure will tend to reflect the recursive structure of the data structure itself. They should go hand in hand in terms of walking the data structure while computing new values or manipulating new data structures. Because this is a new kind of data structure, and because we're creating new kinds of procedures to manipulate them, let's look at this a little more carefully. Here again is our code for count leaves. Those 2 base cases, and then the recursive call, which involves 2 recursions, one down the car of the tree, one down the cdr of the tree. Let's use our substitution model to see how this does the right thing, or at least we hope it does the right thing. And we'll do this in stages. Here's the first simple example. Let's do count leaves on the list of 2. And of course, I'm using list to construct the tree. So this is just a tree of 1 leaf. To be very careful, I'm going to replace the list of 2 with the box and pointer notation so we can see how it's grabbing the pieces. So we're doing count leaves on this structure. What does that cause us to do? Well, equivalently, that's count leaves on the list of 1 element 2. And I'm cheating a little bit here. That's not the procedure application of 2. That's representing a list of just 1 element 2. I check my cases, and the base cases do not hold. It's not empty. And notice I can see that because it's not nil. I also know it's not a leaf because the structure that's passed in is a pair, and therefore leaf does not hold true. As a consequence, I go to the recursive case in which I do count leaves on the car of the tree. Notice the car structure there grabs the element 2. I also do count leaves on the cdr of the tree. That takes the element in the cdr box, which is just nil, and I add them together. Now each of these recursive cases does the right thing. The first count leaves has a single element 2. Is it null? No. Is it a leaf? Yes, because it's not a pair. Therefore I return 1 for that. The second call to count leaves does in fact have an empty tree. It returns 0. And the sum of course gives me out 1. If I look back at my box and pointer diagram, that's exactly right. There's 1 leaf here. So this simple case has worked. Okay, let's try a little harder example. Again, there's my code just like before so you can see it. Let's do count leaves on the list of 5 and 7. Notice what this is. This is a tree whose first branch is just the number 5 and whose second branch is itself another subtree. And it has 1 leaf, 7. If I use my box and pointer diagram to represent this, I'm doing count leaves on the structure shown, a list of 2 elements. This is equivalent to doing count leaves on the list structure shown as the open paren 5, 7, close paren. I run my cases. Neither of the base cases hold here, so I do the recursive call, doing count leaves on the car of the tree. Notice that's going to just be the number 5, it's a leaf. and count leaves on the cooter of the tree, notice the cooter of that first box points itself to a list. So it's a subtree. And that we see is shown by the fact that we have open paren 7 closed paren as the element passed in. I'm going to take the sum of those two things. Doing count leaves on 5, well, that's pretty easy. The base case says it isn't null, but it is a leaf. I return 1. The second call to count leaves, notice, is going to be more careful. Is it empty? No. Is it a leaf? No. It's a tree. And therefore, I do the sum of doing count leaves on the car, which is the number 7, and the cooter, which is empty, of this subtree. And then recursively, I do the same things, and I end up with 2, which is what I wanted. Okay, now let's try a full-fledged example. Here's a new tree that has that full structure of 3 subtrees at the top level, 2 of which are just leaves, and another subtree in the middle that in fact itself has several subtrees underneath it. Let's run count leaves on this example. This is going to give me count leaves run on that list structure, and we can notice that it will do the standard decomposition at the first level, which is going to reduce to doing a count leaves on the first element, which is 4, and count leaves on the remainder of that structure. In fact, it's going to count up and give us the right answer 4, but let's see if we can quickly trace how it does this. So here's the first call to count leaves. I've just abbreviated it CL to make life a little easier for me. Being called on this list structure. And I'm putting it in blue just to distinguish that in fact it is list structure and not a procedure call as it might appear. Recursively, we know what this does. It reduces to applying count leaves to the first element and count leaves to the remainder of the tree. So here's that recursive decomposition. I'm going to add up what I get by counting down the first branch, which is count leaves of 4, to whatever I get by counting down the second branch, which is that subtree as shown. Well, doing count leaves down the first branch is easy. That we know by one of the base cases just returns 1. And of course the recursive call over here is going to do the same thing. It's going to reduce to counting down the first element and counting down the remainder of the tree. And now you get the idea. At each level of the tree, we're calling count leaves on the first element of the tree and adding that to whatever we get by counting the leaves in the remainder of the tree. That keeps reducing until we get down to a leaf, in which case we have a 1, or we get down to an empty tree, in which case we have a 0, and eventually those all accumulate together to add up to the things that we want. Of course, not only can we write procedures that directly manipulate trees, we can capture general patterns. Just as we had the notion of map for lists, we have a similar idea for trees, shown here. Here we need to separate out 2 different base cases, the empty tree and a leaf or isolated element of a tree. For the empty tree, we just return an empty tree. For a leaf, we simply apply the procedure. In the general case, we have to be a bit more careful about our data structure. A tree is a list, each of whose elements might itself be a tree. So we can split a tree into its car and its cooter, each of which is a tree. We must then map our procedure down each of these subpieces and then glue them back together. This is different than mapping down a list where we could just directly const the processed first element onto the remainder of the list. Note that induction holds in this case as well. For each of the 2 base cases, we get back an appropriate tree, either an empty tree or a single leaf, which is a tree. In the inductive case, we know that both the car and the cooter of the tree are trees of smaller size, so we can assume that treemap correctly returns a processed tree. Then we know that const will glue each of these pieces back into the larger tree, and hence by induction this code will correctly process trees of all sizes. We can capture higher order operations on trees beyond just mapping. For example, this code allows us to specify what operation we want to apply to each leaf of the tree and how we want to glue the pieces together. Using this, we can map procedures onto each element of the tree, or we can count up the number of leaves in a tree, or we can reverse the elements of the tree, both at the top level and at each subtree.